Okay, let's get started. So some announcements. First of all, you know the problem set assignment document that's got all the assigned problems in it? You'll notice I've written, I did this some time ago, I don't do this anymore. I've given you the even numbered answers in there. Anybody look at it? You should look at it. And I state the odd answers to the odd number problems are in the back of the book, okay? So you have the answers to all of the odd problems, and you have the solutions. Do you just have my solutions? Did I put, there are other solutions. Sometimes, has anybody looked on Sakai? Oh man. What?
I've downloaded everything. I haven't looked at most of it.
Okay. Well, I just want you to know that there are other solution sets, partial or something. KFCS did some that are typed, but not all of them. And then I got some from Professor Baker. So I think I have those all assembled into by chapter or something like that. But if you're not happy with the solution, with my solutions and knowing the answers, let me know, right? And if you see any problem, when you're going over this more carefully, see any problem with my solutions, let me know. Okay, the other thing is distance learning students will do the problems, scan them, specifically make a PDF. PDFs work. I really just want PDFs when you scan. This is not for the resident students. And you'll upload them into Sakai. There are I just created this morning assignments in Sakai. Oh, they'll just go live just in a couple minutes ago. So right now in Sakai there's 2 assignments, problem set 1 and quiz 1. And that'll allow the distance students to upload those documents and put them in, and I will grade them. Okay, check off the homework and grade the quizzes. But you guys, it's all going to be handled directly, right? You can submit homeworks and quizzes before class, after class, or to my office. If the door is closed, you can slide it under the door, right? Okay. I found that I have to say that, even probably I've said it before, but because I'll get a question in a couple weeks from now, you know, I couldn't turn something in because your door was closed. Okay? Right? You can slide it under the door. All right. Okay. All right, so anybody have any, before we get started, any basic general questions or issues? Start working on experiment 1, right? If you got questions, let me know. Okay, so this is the first problem set. These are pretty easy problems. There's one interesting one more difficult one, spring mass. Actually, this is interesting too, and useful. So if you look at, I didn't draw the diagrams here, but there's different ways that we can have masses and springs connected here, as shown in this problem. First, let me remind you what we derived, and that is that when you have a mass-connected spring, whether it's suspended in a gravitational field or not, it doesn't matter. A constant force does not affect the frequency. The frequency is given by, the angular frequency is given by the square root of the stiffness divided by the mass, right? Okay, so here's some, yes?
Just a quick question. At the answers, at the back of the book, there's a 1/2 pi in front of the answers. It says the natural frequency, and I'm a little bit confused which one is the natural frequency, F or omega?
Yeah.
Because there is a
natural frequency is the same as frequency, and it's F, okay? So I didn't realize that, but you're right, they do say natural frequencies.
Yes.
Why are they using the word natural? They really shouldn't be doing it at this point, but they're doing it because this is just the beginning. We're going to derive this at a frequency. So the word natural is usually used to distinguish the free frequency when it's not being driven. And after a while, you won't worry about the distinction between omega and F anymore. We just use them interchangeably, but when you do anything quantitative, you've got to realize there's a factor of 2 pi in there, right? So they've dealt with I'm going to deal with just, I can see here that I just have the angular frequencies, right? And the frequencies, or natural frequencies, will be 1/2 pi.
Yes, because at the problem 3.2, If you choose F, the answer is gonna be different, I think. So, if you choose omega.
Let's wait till we get to that problem.
Okay.
Okay? Are you okay now in this problem?
Yeah.
Okay, all right. Okay, so the interesting thing here is what happens when you connect two question? Sorry?
He was asking when this is due. This will be the Friday after this Friday.
Yeah, it's next. It's always the following week, when the week that we discuss it, and it's at the end of the week, right? And it's not a real hard deadline, but you don't want to get behind. That's not good.
Right.
Okay. Okay, so I'm sorry I didn't sketch these, but if you look in the book, the first situation here is what happens when you have two identical springs in parallel. So now we're going to add another spring right here in parallel, right, with the same stiffness. What's the frequency going to be? How's the frequency going to change? First of all, qualitatively, is it going to go up or down? Yeah, it's stiffer, right? And what is the way you want to look at this is there's going to be some equivalent, we put another one on here. This is the same mass, okay? I'm not changing the mass. The way you want to look at this is that you want to ask, what's the equivalent stiffness here? Any arrangement of springs here is going to be equivalent to a single spring. And what is the stiffness of that spring? Well, you know, when I pull this down, there's now twice the restoring force. At any position here, if I lift it up or put it down, the force is being doubled by the presence of that other spring. So what's the effective stiffness here? Simply twice the spring stiffness. That's what I wrote here. Okay, so in this case, when you have springs in parallel, their equivalent, identical springs in parallel are equivalent to a single spring with twice the stiffness, because you get twice the force. So the Hooke's law here is going to have the stiffness for the equivalent stiffness for a single spring here is going to be twice the individual stiffness there. All right, so therefore the frequency is going to be the square root of 2s. We use the equivalent stiffness here of twice the individual stiffness, and we get this. All right, so the frequency goes up by the square root of 2 in this case. Anybody have any questions about that? All right, now what about if we, this is easy, if we double the mass, instead of doubling the stiffness in parallel here, now we're going to double the mass. Add another mass here. So now what happens to the frequency? It goes down, there's more inertia, and it's going to go down by the square root of 2, right? Because the effective mass is just, we can still use this, we just need to put in, you know, the total mass here. It's going to be twice the mass. So now the frequency is going to go down by the square root of 2. Anybody have any questions about that? Okay, and now the interesting one. What happens if you add the spring in, well, they're all interesting, I think, actually. This is a little bit more challenging. What if you add the spring in series rather than in parallel? So now we have a spring like this of stiffness S, and we've got another one here. So I've got S here and S here. Now you can start writing down equations, but it's a little trouble. You just want to think about this. Hooke's law is going to hold here. The force is going to be a restoring force proportional to the displacement. When I pull this down a distance x, right? And that's what's important for Hooke's law here. What happens to these springs? They stretch. How much do they stretch?
Half.
That's right. Each spring is going to stretch 1/2 x. So what's the force here going to be? The force here is due to this spring. What this mass sees actually is just this spring. It really doesn't see this directly. When I move this down a distance x, this spring stretches half the amount, because this will be half the amount. The total will be x. Total has to be x here. So what's the force? If I pull this down a distance x,
Minus S over 2.
what is the force compared to the force for a single spring?
Half.
It's going to be half. And that's going to be true no matter what x is here. The Hooke's law here, we're again going to have the force is proportional to the displacement. But the restoring stiffness here is half. And incidentally, this is qualitatively obvious. Maybe you've never done this, but if you take two springs, let's say they're identical, well, we can generalize this, but let's say they're identical, that's in this problem. If you take two springs and each of them have the same stiffness and you feel the stiffness, when you connect them in series, it's definitely less stiff. Has anyone ever actually, you've never done this? Maybe you never have. See, I'm biased because I run the demonstration lab and I do this kind of thing all the time, right? Yeah, so, yeah, maybe I should have brought some springs in, huh? Passed them around. I should have done that. Yeah, and likewise, when you have this situation, when you take two springs and you put them in parallel, it's stiffer. You can clearly feel that it's stiffer. I mean, you really feel the difference. And it's a factor of 2. Okay, so the frequency here, in this case, because the frequency is going to go down, and it's going to go down by the square root of 2. There's going to be a 2 down here, because the effective stiffness is 1/2. Okay, finally, what happens when we have this situation? Here's the final situation. We have S here, M here, and another spring here. So, what's going to happen here when we look at oscillations? Well, it's convenient here to imagine the springs are unstretched in equilibrium. Oh, assume this is horizontal. Gravity is not going to change the frequency, right? Any constant force is not going to change the frequency. So imagine this is the top view and you're looking at this on some frictionless surface. Imagine the springs are unstretched in equilibrium, so that neither are exerting a force here. I displace this, what's going to happen? I get a force this way, what happens here? Same force, same magnitude, same direction as that force. So the force gets doubled. So we're back actually to this case. It's
part A, right?
yeah, it's actually, I don't know how to say this. You get the same answer as part A. It's a similar situation. They're physically distinct situations. You know, we have the spring here. One case we have the spring attached here in parallel. Here we have it here on the other side, which may look like series to you, but it's not, right? It's a difference putting, I never thought about this before, it's a big difference putting the spring here and putting it up there, right? So, but the frequency of this arrangement is going to be the same when the springs are in parallel. Now, what happens if the springs are stretched in equilibrium, which is commonly the case in practice? See, we just imagined, we got at the answer here by imagining that the springs were not stretched in equilibrium.
Shouldn't matter.
That's right. It's not going to matter. And we actually talked a little, we didn't prove it, but we talked about it before in lecture when I mentioned that, you know, with the demonstration I mentioned that in the presence of gravity this is going to sink down, but it's just a constant force. The spring will balance out gravity. It's not going to matter. If you stretch the springs in equilibrium here, all that's important is the change in distance here, and the force that arises when you change the distance. It's going to be the same answer. Okay, well this sometimes comes up, and will come up this quarter, I think. This is useful to realize these simple, different situations here. Anybody have any questions?
The only one that would be considered a coupled oscillator is this last one, right?
We're not doing coupled oscillators here. You're getting your thesis research mixed up with the class research, okay? And I can understand that. Believe me, I understand it completely. I do the same thing. This is a single oscillator here. There's just one frequency. And that's a good question. You can be fooled. You can think, oh, we've got more degrees of what we call degrees of freedom. Have we talked this? We haven't talked about that in this class. There's just one degree of freedom here. Interesting things happen when you have another degree of freedom. And for those of you who took the mechanics, the 3000 level mechanics course last quarter, there's a whole chapter on that in Taylor's book, right? So we're not going to do coupled oscillators where you have more than one degree of freedom here in this class. We need to get into waves. Our goal is to get into waves. There can be coupled waves, and that's the subject of part of Michael's and Kevin's theses. And we're not going to, we just can't do coupled waves. Okay, any other questions or comments? Okay, the next one, I think this is pretty easy. Now, see, I warned you about this. Look at the first sentence. This is 1.32. A simple oscillator whose natural frequency is 5 radians per second. Okay? So you wonder what the word natural is doing there. I already mentioned why that's there. And you'll notice they don't have the word angular there, do they? They're very common. This is clearly the angular frequency because it's in radians per second. So you need to recognize that. So, and people do this all the time. You know. So we've got a simple harmonic oscillator, mass on a spring. We're pulling it aside. Now they say a distance of 3 centimeters. Are we stretching it or compressing it? Right? Here's the situation. We're going to look at oscillations here. And we're given the fact that we're given this number, what are we given here? Oh, it's 5 radians per second. So I just want to point something out here. It's not a big deal, but they say it's displaced a distance of 0.03 meters from its equilibrium position and released. Does that uniquely specify? No. We don't know if it's positive. We don't know if it's pulled over here or compressed. I just want to point that out. So, but we'll assume it's positive, okay? Let's assume for definiteness, because we may need the amplitude. Oh, it's okay, it's not going to make a difference in the questions they asked. But to be definite here, I'm going to assume it's positive, just in order to write down, to make it definite. Okay, so the first part here is from its and released. Find the initial acceleration. Initially there's a force, so there's going to be an acceleration. Don't confuse that with a velocity. What's the initial velocity? 0. That doesn't mean there's no acceleration. So here are what we call initial conditions here. We could go to the solution for the acceleration, but there's no need to here. We can just use the equation of motion. It's usually called an equation of motion. It comes from Newton's second law and Hooke's law. You can see that this is the acceleration, so we can solve for the acceleration. So at t is equal to 0, when the mass is released from rest, the initial acceleration, I'll put a 0 here to denote the initial acceleration. That's an equal sign. Sometimes this happens. I don't understand it. It looks fine in the notes here, but this is some PDF thing, or this, I don't know. That's an equal sign, okay? We can just evaluate this. We know omega naught. It's 5 radians per second. So we evaluate it, we get minus 0.75 meters per second squared. That's the initial acceleration. This is pretty easy. What's the amplitude? You don't have to think a lot about this. What's the amplitude of the motion? I mean, we pulled it aside 0.03 meters. That's going to be the amplitude because we released it from rest. What if we didn't release it from rest? What's the amplitude going to be?
Depends on pushing.
Do we know? Well, we have to be given what that velocity is. Oh, I don't want to say any more because I'm getting close to a problem on the quiz. Okay, I'm going to shut up. Right, so because we're pulling it aside and releasing from rest, obviously the amplitude of the motion is just going to be this 3 centimeters here, otherwise known as 0.03 meters. And now here's something you want to get used to. I don't know if I made a spiel about this or not, but when we're doing oscillators, we're going to get into waves, and amplitude's going to be important. There are different types of amplitude, and you want to think of them all as sort of interchangeably, especially when we get to transducers, which is 4454. Most people think of displacement amplitude here, but there's another kind of amplitude. There's the velocity amplitude. And we showed for simple harmonic motion, it's very easy to show, and you can look back in the notes, that this is the relationship between the displacement amplitude and the velocity amplitude. Right? What about acceleration amplitude? Oh yeah, there's an acceleration amplitude. Anybody know what that's going to be? Take a wild guess. You can probably, pardon me?
Another omega naught.
Another factor of omega naught, right. And it really has to be by dimensional reasons, but you, again, you can just get this, it's a property of simple harmonic motion. So this will become particularly important in transducers. People who do transduction, it's convenient. It's not always convenient to do displacement amplitude. There's a velocity amplitude, there's an acceleration amplitude. Oh, maximum speed here is identical to the velocity amplitude. Okay, any questions about that one? Okay, so now the challenging one, the effective spring mass. This can be done in different ways, and it can be somewhat complicated, but it simplifies in the case where the mass on the end is large compared to the mass of the spring. So we're going to make that assumption here, that the mass of the spring is light. Is that what happened in the experiment last Friday? Anybody remember? What was the smallest mass you hung on the end there? 200 grams? Roughly?
To get it displaced, it was like 300.
Okay, roughly 300 grams. What was the mass of the spring?
Like 70.
It's like 128 with when you combine it with the hanger.
It's about 8 grams.
Okay, wait. The hanger is part of the hanging mass. It's not part of the spring.
That was 50, the spring.
Don't include the hanger in the mass of the spring. That's not going to work, because we're assuming the mass of the spring is all spread out uniformly. If you've got an attachment here and you're considering that to be part of the spring, that screws things up. So what was the mass of the spring roughly?
75 grams.
Yeah, so, you know, it's not very small, but this greatly simplifies the theory, as you'll see. So this is going to be not completely accurate for your experiment. It'll get more accurate. The heavier the mass on there, the more accurate this theory will be. Okay? But you want to recognize that this is approximate for your experiment. It's just an approximate. So people, when they do stuff like that, just keep it in mind. When they start to see screwy things in data, when the data is supposed to lie in a straight line, and they start to see some curvature at small mass, you want to think, oh, it could be due to this. The spring mass behaves simply only in the limit where its mass is small compared to the mass on the end, as we will see. It can be solved in general, and I've done it, but it's a little nasty. Okay, so here's the situation. We're going to assume, incidentally, that the spring, these little links on the end of the spring are small. We don't want to deal with this kind of a situation. Okay, we can, it just gets a little bit more complicated. Now the springs that you had in the lab were, I think they didn't have this, right? They were pretty much like that. There were just, there were little hooks, little curved elements on the end, okay? Which is, yeah, this will mess this, what we're trying to prove here, up. And you'll see it in the theory, actually, if you look at it. So we're going to assume it looks like I've drawn it here. Now, when the spring mass is small compared to the mass on the end, the spring, when the spring mass is 0, how does the spring stretch and compress here? It does so uniformly. So the distance between these turns here, this distance, it's going to be the same. That's what we mean by uniform stretching and compression. If I statically take a spring and stretch it, the distance is going to be the same from one turn to the next. That's the uniform compression. That's going to approximately hold here. It's not going to be exact, right? In fact, for an actual spring with mass, with this thing oscillating, focus your attention on, let's say, this turn right here. Okay? Is this distance going to equal this distance? Which way is it going to go? See, the key here is that this turn has mass. We're focusing our attention on a single turn. It's got mass. If that mass is going back and forth in uniform circular motion, there's got to be a force. There has to be a force. So when this thing is stretched out here, this distance has to be a little bit bigger than that distance. So there'll be a net force on this. Now you can start to see how this can be a complicated problem from a dynamical point of view, from a Newton's second law point of view. But we can avoid it with an energy approach. And this is actually often the case, not just in acoustics and oscillations, but in quantum mechanics. People do the same kind of trick. So we're going to take an energy approach, and we're not going to have to worry about that, as you'll see. But I just wanted to point it out here that once you have mass in that spring, it can't be uniformly stretched. Because you've got an element of mass in the spring, let's say one turn going back and forth, there's got to be a force on it because it's got a mass. So the spring will not be uniformly stretched and compressed. But it turns out we're going to be able to sidestep that with the energy approach. So here's the idea. We're going to look, energy conservation tells us that the maximum potential energy, which occurs at the turning points here, when the mass is going like this, there's a turning point here and a turning point here. That's where the kinetic energy is 0. There'll be a maximum potential energy. It will have to equal the max. There's a maximum potential energy. It will have to equal the maximum kinetic energy when it passes through equilibrium, right? Because energy is constant. So this is a trick that I think Rayleigh, the parent of modern acoustics in the late 1800s, discovered. Approximation method. And it carries over to quantum mechanics to use this idea. Okay, so we're going to be able to get the answer just by writing down expressions for these and equating them. So let me show you how this works. What's the maximum potential energy? Well, it's just going to be this, right? Now again, this is approximate. This is what you get if the spring were uniformly compressed. It's not. So this is just an approximation, but it holds for this in this limit here when we have the spring mass is small. So we just use the normal massless spring result for the maximum potential energy. What about the kinetic energy? As the mass passes through equilibrium, that's where the maximum kinetic energy occurs. What has kinetic energy apart from this mass? The elements here. That's what we need to calculate. So here's how we do it. This mass here is going to contribute, when it passes through equilibrium, it'll be 1/2 the mass times the velocity amplitude squared. And remember, as I just said, the velocity amplitude is this. And we need to add the kinetic energy of the spring. So how do we do that? Well, we have to integrate here. There's no way around it because the mass elements of the spring here are moving. When the mass passes through equilibrium, mass elements here are going to have nearly the same velocity as here. But what about mass elements down here? We talked about this in lecture. How much kinetic energy do we have here? Very little, because it's tied down there. It's not moving. So to find the kinetic energy here, we have to integrate over all little mass elements. So each element will contribute to the kinetic energy 1/2 times its mass times the square of whatever the velocity is in equilibrium. And that varies. Out here it's equal to capital U, right? So here the velocity of the spring is capital U. Let me make sure I'm using this notation here. Yeah. Here the velocity of the spring is approximately 0. The mass here is going to be moving at approximately that velocity. Here it's approximately going to be 0. So how do we need to be able to calculate how the velocity varies through the spring here. We can do that approximately because it's going to be approximately uniformly, it'll be uniform. At this moment here, let's say we're saying this is equilibrium. We need to find the velocity here. It'll be uniform, the distance between the turns. So that means that the velocity has to increase linearly with x. X is the distance. This is x. Oh, we're using x to quantify what's going on with the spring here. This is x equals 0. Oh, there we go. Yeah. Okay. We don't need to worry about the coordinate of this mass. We've been using x for that. For this problem, we're using x to quantify an element of mass here. X runs from 0 to L when the mass is passing through equilibrium. And because it's approximately uniformly, it's approximately uniform. I don't want to say stretched because this is equilibrium. It's not stretched or compressed, okay? But it's going to be uniform. So we can write this down. The velocity of the spring will be 0 at x equals 0, and when x is equal to L, it's got to be u, and it's going to be uniform. So it's got to. This is it. This is what it's got to be. All right. So this is the hard part of the problem is believing this. The rest of it is we're just sort of turning the crank. So we find the kinetic energy. We substitute this into here. And we need to integrate overall mass. Well, that's not good, is it? We want to put it on a calculus level. We need to convert the mass. We have to have one variable, which we're going to choose to be x here. So we got to get rid of this. We got to turn this dms here into dx. We do that with the density of the spring in equilibrium. A little bit of mass is the mass per unit length, the linear density, times the length. Right? And the mass per unit length is going to be the total mass divided by the total length. So this tells me what the little element of mass of the spring here is in terms of dx. I got to go to dx here because I got to do an integral. So I have to go to dx. To connect it with the amount of mass in there, I use the mass per unit length. You've seen this before. Maybe it's been a while. So the mass per unit length is just the total mass, because it's uniform, be the total mass divided by the total length. Okay, so we take this, substitute it in there, take this, substitute it in there, and we integrate over the whole length of the spring when the system's passing through equilibrium. And everybody can do this. We end up having to do the integral of x squared, which is 1/3 x cubed, right? That's easy. The hard part is setting this up, right? That's where you have to think. And I can tell that this is a little confusing to some of you, it seems. I don't know. It's hard to read you. But, it takes thought, and you want to be careful. This is where you can make mistakes. Okay, so this is straightforward. At this point, we integrate, and look what happens. Because of that 1/3 right there, we get this famous factor, right? 1/3. This is where 1/3 the mass of the spring comes in. Why can't we have this? We talked about this in lecture, but why can't we have this without that? That would mean all of the mass is participating in the motion. It's not. We don't have very little energy down here because it's not participating in the motion. It has to be between 0 and ms, and it happens to be 1/3. Okay, so the maximum energy of the system, when the mass passes through equilibrium here, we have the kinetic energy of the mass on the end, and now here's what the spring contributes. It's 1/2 times 1/3 its mass times this. At this point, it's natural to factor out a 1/2 u squared and define the effective mass here. It's just very natural at this point to define an effective mass. And you can see that that effective mass is just the mass on the end plus 1/3 the mass of the spring. Now we're not done. It's tempting at this point to just take that effective mass and substitute it into here. But we really need to show that, okay? And there's different ways of doing this. The way we're going to do it here is, we know that the maximum potential energy has to equal the maximum kinetic energy. So when we set those two things equal, we talked about this first, we just derived this. We set these equal, and we use the fact that for simple harmonic motion, the velocity amplitude is omega naught times the displacement amplitude. We use that fact, substitute for u here, we can cancel the amplitudes and we get what we strongly suspected. At this point, as I just said over there, at this point, this is what we expect, but we really need to prove it, and this proves it. Okay. Instantly, another limit that people deal with, besides this limit that we just talked about, there's this limit where you just have a spring with nothing attached to it. That can be solved pretty easily. It's the in-between case takes more effort. I don't think this is going to come up in this course, but if you're interested, play around with it. Now is the spring stretched uniformly? No way. No, it's going to be, they'll have this differential stretching like we talked about before, and you have to actually calculate it. There's just no way around it. You're going to have to calculate it. In fact, well, I take it back. We are going to talk about this, although it may not be explicit. If I just have a spring here, oscillating back and forth, we have a name for this. Anybody know what it is? It's a standing wave. This is a medium here, and we have a standing wave. And this will be a quarter of a wavelength. So you can actually calculate it in this case. And we will learn how to do that. I don't think we'll do this problem, but it would be a good problem. It should be in the book, but I don't think it is, or I should have asked it. Maybe I'll put it on change one of the quizzes and put it on a quiz. We'll see. Okay, any questions about this? So you're going to use this in the analysis of the first experiment, this approximate result, right? Any questions or comments? Okay, the rest of these, the rest of the problems here are, this is just to refresh your memory. So I think Alex has dropped the, anybody know Alex Baines?
I'm Alex.
God, sorry.
It's okay.
I thought you were somebody else. We're missing a student.
He usually sits here.
Who's that?
Adam Zell.
So you're Alex Baines. I thought it was somebody. Pardon me?
Oh, the other Peruvian.
Okay, all right. So, okay, sorry. Okay, so the rest of this is, the problem set is just simple, complex arithmetic. It's just going to be, it's just a review. But again, it's indispensable in oscillations and waves. So you want to make sure you get it right. So I'll move a little bit more quickly than I'm going to do this. But if you have questions, you can ask me. And you can always, send me an email message or drop by my office. So the first one here is 5.1. Oh yeah, this is good. This is something you need to get used to. Okay, so we have an oscillator here. An oscillator goes like this, but for convenience, theoretically, we've turned the simple harmonic motion into uniform circular motion, right? That's what you can think of. In the complex plane, this is a point going around in the complex plane with uniform circular motion. And what we're interested in is the So this can be omega t. Sometimes we put in a phase. Yeah, in general there can be a phase here. Because at t is equal to 0, it can be anywhere on the circle, right? So we're going to put a plus sign here. So this point here, we're thinking of this as moving in the complex plane. Here's the real axis and here's the imaginary axis. And it's moving with, I guess, omega naught. Is it omega? Oh, we're going to call it just omega here. Okay. So the first thing is to notice this. The real part of this is equal to that, obviously, right? Because we take, we have some amplitude here. And we project it onto here. The real part will be given by this expression. And you know that because e to the I theta is cosine theta plus I sine theta. If we square it, we get this. If we square the complex displacement here, that's what the underscore here is, means it's complex, we get this. Okay? If we then take the real part, you can see that we're just going to get this. When we take the real part. Because the cosine, e to the I theta, the real part's going to be the cosine of theta. And theta is this in this case. Now let's suppose that we do these, there's two operations here. There's squaring and taking the real part. We first squared it and then we took the real part. What happens if we interchange that? And this is going to be important for us later on in this course and other courses when we deal with energy, which involves the square. So this, it turns out, I'll tell you right now and I'll remind you when we hit it later on in this course and the next course, there's a little bit of a price, there's a price to pay for everything. I don't know if you've noticed in life, but anything that looks good, there's always going to be something negative about it. Okay, that's about the only thing I know about life. Right. Okay, so there's a little bit of a price to pay here, and some of you may see what's going to happen here. We squared the complex number and took the real part. Now let's interchange the operations. Let's take the real part. Let's take the real part and then square it. So here's the real part, and now I'm going to square it, and I get this. Now we can decompose this using a trigonometric identity. Cosine squared of theta is 1/2 times 1 plus cosine 2 theta. That's a trigonometric identity. In waves and oscillations, you will, after a while, you won't think of it as a trigonometric identity. You'll think of it as a Fourier expansion. Okay? We think of this as a wave, and its decomposition is a constant plus twice the frequency. But don't worry about that right now. Right now, just think of it as a trigonometric identity. So let's review here. This is the real part of the square. If I take the real part first and then square it, I get this. Do these two things equal each other? No, in fact, you'll see, and the way I've written it here, this may be a little confusing. This term right here gives us that. So these are different. They're definitely different. They're different by this constant term here. So mathematicians and physicists have a great way of saying this. These operations, in this case, the operations of taking the real part and squaring do not commute. It depends upon the order that you do them. And there are some things like this, and this is an example. Sometimes operations, in a moment we're going to see an example where they commute. But in this case, they don't commute. And it's important for us, and again, don't worry about this, I will remind you when we hit it, and we're going to hit it in a number of cases. When we want to deal with energy, the temptation, when we're dealing with complex numbers, is just to square this. But we have to take the real part first, because the operations don't commute. The real part of the square is not the square of the real part. And that's what's physically relevant. We have to take, we have to take the real part, because what we're interested in are the oscillations here. Okay, but again, don't worry, I'll remind you when we hit this. Any questions or comments? Okay, these final two, we're okay, I think. Again, this is pretty simple. We have two complex numbers here. You can always write any complex number as an amplitude and a phase. Okay, and you can also write it as a real and imaginary part, and that's going to come up in the next problem. So here are these two, these are two, you can think of these as simple harmonic motions. We've gone complex here, converting this simple harmonic motion to uniform circular motion in the complex plane. What's the product of these two? Well, you can see it's very easy in this representation. It's just the product of the amplitudes. Incidentally, because we're doing oscillations and waves, we'll think of these as amplitudes and think of this as a phase. In the complex analysis language, this is a modulus and this is an argument. Okay, so they have different words, they both mean the same. And sometimes it's convenient, and sometimes I'll say that. And there's going to be a point, well, we're going to get to it right down here. Okay, so, but they mean the same thing. We'll tend to talk about amplitudes and phases because we're interested in oscillations. So here's the product of these two complex displacements. It's equal to this. If I then take the real part, you can see that I get this. This is similar to what we just did. It's just a little bit more general. And by the way, if you interchange these operations here, you're not going to get the same number. You're not going to get the same result. If you take, in other words, the product of the real parts is not the real part of the product. Does that sound good? That kind of rolls off your tongue. And you can practice this at home, okay? The product, let's imagine that we're going to take the real part here. The real part of the product is not the same, excuse me, we did do it here. The real part of the product is not going to be the same as the product of the real parts, and that's what we just saw. Those operations don't commute. This is just a more general thing here. And we weren't asked to do that. What's the ratio? So this is just really simple to make sure you understand how to deal with these exponentials, which is really easy. That's why we use this. These expressions are so simple here. 1 over b, we're going to put a minus sign here because this goes downstairs. So the ratio becomes this. The real part of the ratio, you can see, is going to be this. And oh, now we're finally getting to what's related to this, okay? Here's the real part of the product. Here's the product of the real parts. And you get something, and again, I put this in. That's good, I put it in here. They're not the same. What about these phase angles here? In complex language, this is called the argument. This, you can write any complex number. Often people use z. You can use write any complex number like this, and technically what people use in the language they use for complex analysis is that this is the modulus and this is the argument. Okay, so I'm going to utilize that here because we're asked what the phase angle is. So that would be this argument function here. And you can see very easily from up here, that's going to be the phase. Okay, any questions about that? So the idea of this next problem is it's similar to this problem, except now instead of this representation, the amplitude phase, I'm just going to try to forget about this, okay. The amplitude phase representation, there's the real part and the imaginary part representation. That's their equivalent. Okay, you use whatever's convenient. So that's the purpose of this problem. Now we see we have the rectangular coordinates or representation. And you know from Pythagoras, the amplitude is going to be given by this, right? And we can go through and do these other, I'll let you, yeah, we're just getting late here. So we can find this is the absolute value or the modulus of the product of two complex numbers. And you can see it's more complicated here than it is over there. Oh, look at this. Is the absolute value of the product equal to the product of the absolute values? I've done something here. I didn't say anything about it. So let me write this down. You can show, it's not easy to show with with the real and imaginary parts, but with the polar form here, with this form, it's easy to show that the absolute value, or the modulus of the product, is the product here. You can show that. So in this case, these two operations, taking the absolute value and the product, it doesn't matter the order you do them. See, here I've multiplied it, then I've taken it, the absolute value. Here I've taken the absolute value and then multiplied. I've commuted the operations. It's okay. Sometimes operations commute, sometimes they don't. In this case, they do. Okay, so we're out of time, but this is straightforward. It just looks a little uglier because we're dealing with real and imaginary parts. So people, when they tend to deal with complex numbers, when people deal with complex numbers, they tend to use the amplitude phase representation. But there are times, and we're going to see it in this class, where it's more convenient to use the real and imaginary part representations. Okay? So if you have any questions about this, just drop by or drop me an email message. Okay.